Yeah. So in the last class, we discussed about the spherical surfaces. Now we are learning about the lens. What is a lens? First, know the meaning of lens. Lens means at least one part should be curved. Okay. So like it is a homogeneous optical medium bounded by two surfaces, of which at least one is spherical. So that can be called as a lens. So lens definition, write down. It is the homogeneous, homogeneous optical medium bounded by two surfaces, of which at least one is spherical. One is spherical. So this is the lens definition. So here we have a convex lens, concave, plano convex. Okay, still have that. So first, let's know what is the meaning of convex lens. So convex lens, we also call it as a converging lens also. Convex, we also call it as a converging, because when the light rays passes parallel to the principal axis, so it will converges on the principal axis. Okay, so when it passes through the lens, so it converges at a particular point, and we call it as a focus. So it is the lens which converges a parallel beam of light. It is a lens which converges a parallel beam of light when passes through it. So this is through the light phenomena. Okay, we can tell this, or we can also define that the lens which is bulged at the middle and tapering at the edges. Okay, at the edge it is very thin, but at the middle it is very thick. Okay, this is called a convex lens. So light converge ಆಗೋದ್ರಿಂದ ಇದನ್ನ converging lens ಅಂತ ಕೂಡ ಕರೀತೀವಿ. The next type is concave lens. Concave lens. So here called as a biconcave lens, ಅಥವಾ ಇದನ್ನ diverging lens ಅಂತ ಕೂಡ ಕರೀತೀವಿ. Because when the light comes parallel to the principal axis like this, actually diverges. Okay, light get diverged, but it appeared to meet in front of the lens. So here in this kind of lenses, we get virtual images. Okay, so it is the lens. It is the lens which diverges a parallel beam of light when passes through it. So this is the definition of concave lens. So related to lens, We can have what is the meaning of principal focus. Okay, in the focal length. So this is the point. F, we can call it as a principal focus, even here also. And this is an optic center. Okay. So the distance between the optic center and the principal focus we call as a focal length. Here is optic center. The distance between the optic center and the focus we call as a focal length in the case of lens. Focal length meaning small f ಬರಿಬೇಕು focal length ಗೆ capital F ಬರೆದ್ರೆ principal focus ಅಂತ ಆಗುತ್ತೆ. It is the distance between optical center and principal focus. Of a lens. What is the principal focus? In a principal focus center, it is a point on the principal axis where the light rays actually meet or it appear to meet. So here is the so this is called a principal focus. Understand? It is a point on the principal axis where light actual meet at that point or it appears to meet. Okay, in case of a convex lens, actual meet agutta. In case of concave, it appears to meet. Okay, or it appears to diverge from that point. So that point is called principal focus. You can write that. Principal focus. Capital F. It is the point on the principal axis where the light rays actually meet or appear to diverge from that point. Okay, this is the meaning of principal focus. Understood? Now to understand the derivations regarding to the lens, first important thing is that we have to understand the Cartesian sign conventions used in the lens. Okay, very, very important. Cartesian sign conventions. Even this is applicable for a mirror also. Okay, Cartesian sign conventions. So let us take an example of one convex lens, and here is a principal axis passing through the optic center, that will be okay, principal axis, and this is an optic center. Okay, so whatever the distance we measure, it always must be from the optical center. Okay, all the distances measured from the optical center along the principal axis. Even though you can measure the object distance or the image distance, but you have to start from the optic center only. Got it? And any distances measured in the direction of light. Light direction here ಹೋಗ್ತಿದೆ corona. This is the incident light direction. Whatever the distance you measure in the same direction, That means towards the right side of the lens. Okay, so that will be taken as positive. Got it? Distances along the light direction. Along the light direction, it is taken as positive. Got it? If you measure any distances opposite to the light direction, so it will be taken as negative. That means towards the left side of the lens. Okay. So distances measured opposite to light. Opposite to light direction. And any upward distances. Okay. Upward distances can be taken as a positive, and any downward distances, okay, it can be taken as negative. Downward distances can be taken as negative. Understood? So this is the very important to understand the derivations of lens maker's formula and combination of lenses. So first we have to understand that all the measurements are done from the optic center only, and any distances measured in the light direction is taken as positive, and any distances measured towards left side of the lens, that means opposite to the incident light direction, can be taken as negative, and upward distances taken as positive, and downward distances taken as negative. Very important. Take the information related to the meaning of thin lens. What is the meaning of thin lens? Means the lens whose size is very negligibly small compared to the radii of curvature. Okay, so that kind of lenses we call as a thin lens. So it is the lens whose thickness is negligibly small compared to its radii of curvature. Okay, the thin lens formula can be given as 1 by f is equal to 1 by v minus 1 by u. So this is called as a thin lens formula. See, when I take an example as a convex lens, okay, or a convex lens, so it is imagined to be formed due to the two spheres like this. Okay, hence we can expect the two center of curvature for that. Center of curvature 1, center of curvature 2. And here you will get the radius of curvature R1 and R2. Okay. So one radius of curvature comes towards the right, that can be taken as plus R2. And one radius of curvature comes towards left, that can be taken as minus R1. Understand this? Okay. So this is the biconvex lens. Even the concave lens also, when you take a concave lens, it is imagined to be formed by the two spheres. ಎರಡು ಸ್ಪಿಯರ್ ಇಂದ ಫಾರ್ಮ್ ಆಗಿರೋ ರೀತಿ ಕಾಣುತ್ತದು. ಹಾಗಾಗಿ ಎರಡು ಸ್ಪಿಯರ್ ಇದ್ಮೇಲೆ ಎರಡು ಸೆಂಟರ್ ಆಫ್ ಕರ್ವೇಚರ್ಸ್ ಇರುತ್ತೆ, ಎರಡು ರೇಡಿಯಸ್ ಆಫ್ ಕರ್ವೇಚರ್ ಇರುತ್ತೆ. ಸೊ ರೇಡಿಯಸ್ ಆಫ್ ಕರ್ವೇಚರ್ ರೈಟ್ ಸೈಡ್ in ಬರುತ್ತೆ. ಅಕಾರ್ಡಿಂಗ್ ಟು ಕಾರ್ಟೇಶಿಯನ್ ಸೈನ್ ಕನ್ವೆನ್ಷನ್ ಇಟ್ ಇಸ್ ಟೇಕನ್ as ಪಾಸಿಟಿವ್, and according to the Cartesian sign convention towards left, we will take it as a negative. Depends on how the light falls on the lens. Okay, there will be two radius of curvature, two center of curvature, and we can find two focus also. Yes, shall we move to next concept? That is to derive lens maker's formula. Very, very important. Lens maker's formula. Most repeated question in the board exams. So let us understand the diagram first. So this is the one by convex lens I am taking, and here is a principal axis which is passing through the optic center. This is optic center O, and here I can mark as a point object. Okay, and I'll mark the boundary of the lens as a B, C, and here is a D. ABC ಅನ್ನೋದು ಒಂದು ಫೇಸ್, ADC ಅನ್ನೋದು ಮತ್ತೊಂದು ಫೇಸ್. ಇಲ್ಲಿ ಆಬ್ಜೆಕ್ಟ್ ಇದೆ. Okay, and from the object first light fall on a first face. ಈ ಮೊದಲನೇ ಫೇಸ್ ಮೇಲೆ ಬೀಳುತ್ತೆ. ಮೊದಲನೇ ಫೇಸ್ ಮೇಲೆ ಬಿದ್ದ ನಂತರ ಏನಾಗುತ್ತೆ ನೋಡಿ, from the first phase we gave it gave one image. Okay, so that image is the I1, and ಈ ಇಮೇಜ್ ಎಲ್ಲಿರುತ್ತೆ ಅಂದ್ರೆ ಲೆನ್ಸ್ ಒಳಗಡೆ ಇರುತ್ತೆ. ಅರ್ಥ ಆಗ್ತಿದ್ಯಾ? ಇದು ಮೊದಲನೇ ಫೇಸಿನ ಡಯಾಗ್ರಾಮ್ ಅಷ್ಟೇ, ಇಲ್ಲಿ ಎರಡನೇ ಫೇಸ್ ಇಲ್ಲ ಅನ್ಕೋ. Just forget the second phase ADC. From the first ABC, after refraction of light, I am getting the first image, that is I1. And where this I1 locates? It actually locates inside the lens. And this I1 acts as a virtual object for the second phase. ಈ ಎರಡನೇ ಫೇಸ್ಗೆ I1 ಅನ್ನೋದು ಆಬ್ಜೆಕ್ಟ್ ಆಗಿ ಬಿಹೇವ್ ಮಾಡುತ್ತೆ. Hence, we get the final image after refraction, that is I. Okay. So light direction ಬರ್ಕೋಣ. So optical center ಇದನ್ನು ತಗೊಂಡ್ಬಿಟ್ಟಿದ್ದೀನಿ. ಆಬ್ಜೆಕ್ಟ್ ಅನ್ನ ಇದನ್ನ ನಾನು I'll call it as X. Okay. Optic center O ಅಂತ ತಗೊಂಡಿದ್ದೀನಿ. So I'll call the object position as X. Got it? Now this is the object distance U, and here is a image distance V, and here is a first image distance from the first phase, that is V1. Diagram complete ಮಾಡ್ಕೊಳ್ಳಿ. ಇದನ್ನ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕೆ ಇದನ್ನ ಸ್ಪ್ಲಿಟ್ ಮಾಡಿ ಬರಬೇಕು diagram. I will show you that. So this is a general diagram. Outside medium n equals 1. So for air medium it is. Okay. Illu kuda air ida. I can take generally as a n equals 1 for air. But inside is a glass medium. So refractive index, I'll write it as a n. Or you can also take n1, n2, ಆತರನು ಕೂಡ ತಗೋಬಹುದು. So now we have to apply the general formula. Okay, so last spherical surfaces alli now general formula ಕಲ್ತಿದ್ದೀವಿ. So refractive index of the image space by image distance. Okay, ಅದನ್ನ apply ಮಾಡಬೇಕು. for spherical surfaces. Spherical surfaces. We have the general formula, that is refractive index of image space. Image space divided by image distance plus refractive index of object space divided by object distance. Is equal to difference in refractive index divided by radius of curvature. Radius of curvature. ನೋಡಿ ಈ ಜನರಲ್ ಫಾರ್ಮುಲಾನ ನಾವು ಎರಡು ಫೇಸ್ ಕೂಡ ಅಪ್ಲೈ ಮಾಡಬೇಕು. ಇದನ್ನ ಈಕ್ವೇಶನ್ 1 ಅಂತ ತಗೊಳ್ಳಿ. Please copy this. In diagram, X is an object, I1 is the image from ABC first phase, and I is the image from ADC. N refractive index is object distance, V is an image. Now let's apply this general formula for the two phases. Now I'm applying for the first phase, that is ABC. Okay. So for the refraction at phase ABC, in absence of ADC, in absence of ADC. So imagine there is no second phase. Okay. Refraction at phase ABC. So again, I will draw the diagram for this. So this is the diagram. A, B, C, and here is an object X. Okay. Now here the light falls on the first phase and it gives the image I1. Okay. Actually, this I1 we shown in the last diagram outside. That means it is, you have to imagine that lies inside the lens. Okay, with respect to this object distance is U and image distance become V1. And image lies inside, so refractive index of the image space is N and refractive index of the object space is 1. So make ready all the data. Refractive index of object space, so that is equal to 1. Refractive index of image space, that is equal to N. Object distance, according to sign conventions, it is measuring towards left, so take it as a minus U. And image distance, so plus V1 out. Therefore, equation 1 becomes, applying the general formula, refractive index of the image space antara, that is N, divided by image distance V1, and refractive index of object space is 1, and image, sorry, object distance minus here, hence it is minus, and then difference in the refractive index is N minus 1 divided by radius of curvature. See, since it is coming, radius coming towards the right side, so here the plus R1, it becomes radius of curvature. Call this one as an equation 50. So this is for the refraction at phase ABC. ಮೊದಲನೇ phase ಗೆ ಸಂಬಂಧಪಟ್ಟ ಹಾಗೆ. Copy this. Now for the refraction at second phase, ADC ಇದೆಲ್ಲ ನಾವು phase ಅಲ್ಲಿ ಮಾಡೋಣ. For the refraction at the face ADC. Now for the second phase, the image I1 behaves as a virtual object. See, this is the second phase, ADC. ಈ ರೀತಿ ಇದೆ ಅದು. ADC. So here is the principal axis. It's going already from the first phase. The I1 already ಒಳಗಡೆ form ಆಗಿದೆ, right? This is the I1. From this, the light ray fall on the second phase and it gives the final image here. So, ಇದರ distance ಏನಾಗಿದೆ? V1 ಇದೆ, right? ಇದರ distance V ಇದೆ. ನೋಡಿ split ಮಾಡಿ ಬರೆದ್ರೆ ಈ ರೀತಿ ಅರ್ಥ ಆಗುತ್ತೆ ನಿಮಗೆ. For the second phase, object is I1, image is I. Object distance is V1, image distance is V. And refractive index of the object space is n and image space is 1. Okay, write all the data. Refractive index of object space, that is n. Refractive index of image space. So image, where it comes, the final image is in outside, that is 1. And object distance, that is minus V1. Okay, here you can write I1 acts as virtual object. ಹಾಗಾಗಿ object distance minus V1 ಆಗುತ್ತೆ because towards the left ಇದೆ. And image distance, so that is plus since it is towards the right. Okay, and what about the radius of curvature now? The radius of curvature, it becomes negative. Okay, minus R2 ಆಗುತ್ತೆ because it is coming towards the left, opposite to the light direction, but the light radius of curvature. Understand? Now substitute in the equation 1, the general formula equation 1 becomes refractive index of the image space 1 divided by image distance V, object space in a refractive index m, and object distance V1 minus V1. So I will turn it. Difference in the refractive index. This difference, higher minus lower, I can write as higher minus 1, no problem. Okay. Now this becomes minus R2. Call it as an equation 3. Okay, this is for the second phase. Copy this. Yes. Now we got the two equations. You can see here. We solve for the two phases. We apply this general formula. Okay. For the first phase, we got equation 2. For the second phase, we got equation 3. Now add these two equations. Okay. Next step, adding equations 2 and 3. Adding equations 2 and 3, what you get? So, N2 by V1 minus 1 by U. This is from the equation 2. For that LHS, I'm adding the equation 3 LHS plus 1 by V minus N2 by V1 is equal to N2 minus 1. Okay. So N minus 1 divided by R1 plus of N minus 1, okay, divided by minus R2. This is RHS of third equation. Now your plus N by V1 minus N by V1 get cancelled. Then we got 1 by V minus 1 by U. Write down 1 by V minus 1 by U is equal to, I can take N minus 1 common here, 1 by R1 minus 1 by R2. Right? Since from the thin lens formula, we know that thin lens formula 1 by F is equal to 1 by V minus 1 by U. Right? Therefore, I can write this as 1 by F is equal to N minus 1 by R1 minus 1 by R2. So this is the lens maker's formula. We also call it as Newton's lens maker's formula. Yeah, please copy this. Yeah. See, from this equation, we can tell that the focal length of a lens depends on the refractive index of the material of the lens and even the refractive index of the surrounding medium. If it is a air, I taken as a 1. Okay, fine. But if it's not a air, then it will be like N2 minus N1. And it depends on the radius of curvature of the two surfaces. And also it depends on the wavelength of the light. Got it? So the focal length of a lens depends on radius of curvature, refractive index of the surrounding medium, and refractive index of the lens material, and also it depends on the wavelength of light. Moving to the next concept, it is about power of a lens. Power of a lens. The concept is power of a lens. Just a minute. The power of a lens we can define like this. It is defined as the tangent of the angle by which the lens diverges or converges a beam of light. Converges a beam of light. Falling on it at unit distance. The meaning is at unit distance from the optical center. optical center. Okay. So it basically an ability of a lens that how much it converges or diverges. Okay. So the light ಅನ್ನ ಎಷ್ಟು bend ಮಾಡುತ್ತೆ ಅನ್ನೋದ್ರ ಮೇಲೆ ನಿಂತಿರುತ್ತೆ ಅದರ power. Okay. So suppose if I take an lens here, convex lens, ಇಲ್ಲಿ principal axis ಇರುತ್ತೆ, ಇದು optic center ಆಗಿರುತ್ತೆ. ಹೌದಾ? Any light which comes parallel to the principal axis will pass through the focus like this. See, this is the one height h we take. And now h ಅಂತ ತಗೊಂತೀವಿ. And here is a principal focus. After refraction, so it has to pass through the focus. Actually, it should go like this. ಈ ರೀತಿ ಹೋಗೋದಿಲ್ಲ. A lens ಏನ್ ಮಾಡ್ತಿದೆ? It is bending with certain angle theta. Yeah. So that ability of the lens to make a light to converge or diverge. So ಇದನ್ನ ನಾವು ಇನ್ನೊಂದು ಹೇಳ್ಬೇಕಂದ್ರೆ tan theta. If I take the tan theta here, if I take the theta according to alternate angle property, the tan theta becomes h by f ಅಂತ ಹೇಳ್ತೀವಿ. Or p is equal to h by f ಅಂತ ಬರೀತೀವಿ. So if h is 1 unit, at unit distance ಅಂತ ಕೊಟ್ಟಿದೆ ನೋಡಿ. At unit distance means the h height value 1 ಆದ್ರೆ unit h is equal to unit distance. Then it will be considered as a just 1. Therefore, we can write as a p is equal to 1 by f. Understood? So this is the meaning of power of lens. ಅಥವಾ ಪವರ್ ಆಫ್ ಲೆನ್ಸ್ ಅನ್ನು ನೀವು ಹೀಗೂ ಕೂಡ ಡಿಫೈನ್ ಮಾಡಬಹುದು. ಸೊ ಇಟ್ ಈಸ್ ಅ ರೆಸಿಪ್ರೋಕಲ್ ಆಫ್ ದ ಫೋಕಲ್ ಲೆಂತ್ ಅಂತ ಕೂಡ ಹೇಳ್ಬೋದು. ಓಕೆ, ಪವರ್ ಆಫ್ ಲೆನ್ಸ್ can also be defined as a reciprocal of the focal length of a lens. Okay, at unit distance from the optical center. So here the power of convex lens is taken as positive. Power of convex lens is taken as positive, and power of concave lens is taken as negative. Okay, yakandra it depends on a focal length, right? So for the convex lens, focal length is positive, hence power also comes positive. But for the concave lens, focal length is negative, hence it comes with a negative sign. So unit of power, SI unit of power, the SI unit of power of lens ನಾವು diopter ಅಂತ ಕರಿತೀವಿ, or we write capital D. Okay, diopter capital D ಅಂತ ಬರುತ್ತೆ. So how to define a diopter? So definition of one diopter. ಹೇಗೆ define ಮಾಡೋದು? The meaning of one diopter. The focal length must be 1 meter. That's it. Power of a lens is said to be 1 diopter if its focal length is 1 meter. If its focal length is 1 meter. Okay. Next, related to lens, we have a definition: magnification of lens. magnification of a lens. We call it as a magnifier power ಅಂತಾನು ಹೇಳ್ತೀವಿ. ಇದನ್ನ linear magnification ಅಂತ ಹೇಳ್ತೀವಿ. Linear magnification. So how to find out the magnification of lens? Object size ಏನಿರುತ್ತೆ ಅದೇ size ಅಲ್ಲಿ image ಬರೋದಿಲ್ಲ ಹೌದಾ? Either it may be a smaller in size or it might be a bigger in size. Okay, so to check that the magnification, we can give the formula that height of the image one, height of the object. You can write like this, or in terms of the distances, m is equal to v by u, image distance divided by object distance. ಈ ರೀತಿ ರೇಷಿಯೋ ಮಾಡೋದ್ರಿಂದ ಕೂಡ ನಮಗೆ magnification power ಗೊತ್ತಾಗುತ್ತೆ. Okay, it is a ratio of height of the image to the height of the object, or it is a ratio between image distance to the object distance. Got it? This is the meaning of magnification. Now for today, we saw one more last derivation. So that is derive an expression for, very important again, even for a 5 mark, expression for equivalent focal length of two thin convex lenses, in contact. Okay, two thin lens, both are convex, right? So ಎರಡು ಕಾಂಟ್ಯಾಕ್ಟ್ ಅಲ್ಲಿ ಇದ್ದಾಗ ಯಾವ ರೀತಿ ಫೋಕಲ್ ಲೆಂತ್ ಚೇಂಜ್ ಆಗುತ್ತೆ. Okay, for a single lens, we know lens makers formula ಗೊತ್ತಿದೆ, thin lens formula ಗೊತ್ತಿದೆ, but now we are placing the two lenses in contact. Okay, let's take the two lenses. Lens 1 convex, thin lens ಮತ್ತೆ ಎರಡು ಕೂಡ. Okay, thin lens ಅಂದ್ರೆ meaning ಗೊತ್ತಿದೆ ನಿಮಗೆ. So both are in contact. Let's check it out. Two thin lenses in contact. So this is the principal axis, and here I am placing an object. So this is the lens 1 and this is the lens 2. So here is the first light falls on a first lens, and then it refracts to the first lens, and it goes to the second, right? It enters to the second, and again it refracts. So from the first lens, it gives the first image, that is I1. The I1 idella, this is the image from the first lens, and final image comes from the second lens, that is I. Again, from like a lens maker's formula, how we derive like that. The first lens gives the image I1, and this I1 acts as a virtual object for the second lens. Okay, so here is the image distance from the point of contact of two lenses. Allinda count ಮಾಡಬೇಕು. ಈ ಪಾಯಿಂಟ್ ಇಂದ ತಗೊಳ್ಬೇಕು ನಾವು reference point to measure object distance or image distance. And V1 here, and here is a U. Okay, so L1 and L2, this is object distance, and image distance is V1 and V. So we can use the general formula for the thin lenses. We have 1 by focal length is equal to, use this as a general formula, 1 by image distance plus 1 by object distance. Object distance. Okay, call it as equation. Please copy this. Applying this general formula for the two lenses. Okay, for the refraction of the lens 1. Refraction at lens L1 in the absence of L2. Okay, so for a moment L2 ಇಲ್ಲ ಅಂತ ಅಂದ್ಕೊಳ್ಳೋಣ. So first lens ಇಂದ ಮಾತ್ರ. Okay, for the first lens ನೋಡಿ ಏನಾಗುತ್ತೆ, focal length f1 ಆಗುತ್ತೆ. Focal length is equal to f1. ಆಮೇಲೆ image distance becomes I1 for the first lens. Okay, image distance is V1 because image we consider as a I1, and object distance become is minus U by the sign convention towards left. Okay, for the refraction of lens L1, so clear work only here. O is the object, and I1 is the image. Okay, so now use the general formula equation 1, substitute that 1 by focal length, it will become 1 by f1 is equal to 1 by v1 image distance and object distance. Call it as equation 2. Now for the second lens, refraction at L2, second lens. Okay, so here in the I1 is the virtual object, right? I1 act as a virtual object, and I is the final image. I is the final image. Therefore, focal length is equal to f2, second focal length, and image distance is equal to V, final image distance. Object distance, the object distance becomes minus V1. Okay, because we consider I1 as a virtual object, right? Now substituting the equation 1 in the general formula, we get this 1 by f2 is equal to 1 by, okay, image distance 1 by V, final image, minus object, that is V1. So this is the equation 3. Now you add the 2 and 3. Adding equations 2 and 3. So when you add the equations 2 and 3, you will get 1 by f1 plus 1 by f2 is equal to, yeah, by adding, see, 1 by v1 minus 1 by u varutte right hand side alli, and plus 1 by v minus 1 by v1. So we can cancel out minus 1 by v1 and plus 1 by v1. So here 1 by v minus 1 by u we are getting, since as we know that thin lens makers formula, right? Thin lens formula, 1 by f is equal to 1 by v minus 1 by u, right? Therefore, we can write this as a 1 by f1 plus 1 by f2 is equal to 1 by F. So where F is called as a equivalent focal length. Got it? Right. 1 by F is equal to 1 by F1 plus 1 by F2. And we can put multiple lenses in contact and it goes on plus 1 by F3 plus so on up to 1 by F1. So that F is called the equivalent focal length. The meaning of equivalent focal length is it is the focal length of a one single lens which gives the combined effect of the combination, like combination of two or more lenses. Okay. So which is equivalent value for the other two. So ಎರಡು ಲೆನ್ಸ್ ಏನಿದೆ ಅದಕ್ಕೆ ಸಮ ಅಂತ ಅದನ್ನ ಈಕ್ವಿವೆಲೆಂಟ್ ಫೋಕಲ್ ಲೆಂತ್ ಅಂತ ಕರೀತೀವಿ. So this is also and final derivation. I will explain once again. See here. Two thin lenses are in contact. So there are lenses L1 and L2. For the lens 1, O is the object, I1 is the image. For the lens 2, I1 is the virtual object, I is the final image. So this is the general formula we are using. 1 by focal length equals 1 by image distance plus 1 by object distance. Apply this formula for the two lenses separately. Now for the first lens, when you apply, focal length becomes F1 and image distance becomes V1. Object distance is minus U. Right? Substituting the general formula, you get the equation 2. Next, for the second lens, I1 acts as a virtual object, I is the final image. And focal length for the second lens, we can take it as F2, image distance is V, object distance is minus V1. Substitute that in the equation 1, then you get third equation. Adding these two equations, add them, left hand side and right hand side. 1 by V1, 1 by V1 get cancelled. And here 1 by V minus 1 by U can be written as 1 by F. So this is the thin lens formula. You can write here from thin lens formula. Okay. So take this as a 1 by F. So the equivalent focal length becomes 1 by F equals 1 by F1 plus 1 by F2.